Okay. Well, thank you all very much for joining us today. We're very pleased at Foresight to be hosting this Hydrogen 101 workshop in collaboration with our funders at the BC Clean Energy and Major Projects Office. We're very happy to see strong interest from all of you and look forward to your participation today. So this webinar is produced for residents of BC's Kootenay, Thompson, Okanagan, and Vancouver Island regions, and is part of a series that we are running and have been running over the last year that seeks to grow awareness of hydrogen and its role in BC's low carbon energy future. So we're going to discuss the future of hydrogen in BC, including transportation considerations and potential sources of supply and demand. Before we move ahead, I'd like to first acknowledge that the lands on which Foresight's BC office is located are part of the traditional unceded territories of the Musqueam, Squamish, and Tsleil-Waututh nations, and has been stewarded by them since time immemorial. The term unceded acknowledges the dispossession of the land and the inherent rights that the Musqueam, Squamish, and Tsleil-Waututh hold to the territory. And I'd like to also acknowledge that Foresight operates nationwide and that we acknowledge the traditional owners and caretakers of these lands. So the goal of today's workshop is to build a greater awareness and understanding of hydrogen and the opportunities that it presents for BC. The majority of the session will feature a Hydrogen 101 presentation where we're going to share some background information on hydrogen, including some of its potential roles in the local energy transition. Throughout the session, we'll have a few poll questions for you all, so please keep your eyes out for those. And please feel free to share any questions you have in the Q&A box at the bottom of your screen, and we'll respond throughout the session. A bit about our agenda for today. Before we begin the presentation, we'll start with some introductory remarks about Foresight. Then I'll pass it over to my colleague Colton for an overview of all things hydrogen. We're also here from my colleague Aislinn on some considerations for the transportation of hydrogen. Then we're going to be hearing from our friends at UBCO for a bit of context for interior BC, followed by HTech for Vancouver Island. We'll close up at just before 11:30. For those of you who are wondering who we are, a bit about Foresight. We're Canada's largest clean tech innovation and adoption accelerator, and our purpose is to help the world do more with less in a sustainable way. We're a nonprofit organization that operates across the country, but we got our start here in BC. We connect public and private sectors to the world's best clean technologies. We support both the supply and demand sides of clean tech in Canada through venture acceleration and adoption support. We work across many sectors in clean tech, so we define clean tech in a very broad way as any technology that can help reduce environmental impact and support industrial productivity. And hydrogen is one of our areas of focus. So we've done several projects over the last few years with industry, First Nations, and government looking at opportunities around hydrogen in BC. Some of our impact is highlighted here. We've supported almost 1,300 companies to generate over $500 million in revenue and almost $1.8 billion in capital support. We've run 61 industry challenges, created over 8,700 green jobs, and contributed to the reduction of a projected 70 megatons of greenhouse gas emissions. And now I'd like to pass it off to Colton to give us an overview of today's session.
Thanks very much, Alyssa. Welcome, everybody. Again, thank you very much for being here today. So before I get into the background of our Hydrogen 101 presentation, I'd first like to provide a brief overview of our partnership with the Clean Energy and Major Projects Office. So to start, on March 14, 2023, the government of BC announced the New Energy Action Framework with a commitment to establish a Clean Energy and Major Projects Office. For those of you that aren't familiar, CEMPO works across government to help clean energy projects reach final investment decisions and support tangible benefits to BC and Indigenous communities. CEMPO supports the development of a wide range of new clean energy projects, including hydrogen, carbon capture, utilization and storage, renewable fuels, and emerging energy storage technologies. CEMPO also supports the implementation of key policy actions within the BC hydrogen strategy, which we'll talk a little bit more about. Our partnership at Foresight involves the completion of opportunity assessments exploring the development of hydrogen hubs in 4 economic regions of the province. So the first being the Lower Mainland, Northeast BC, the interior BC, so that's including the Kootenays and the Okanagan, as well as Vancouver Island. We're in the midst of finishing up our final two opportunity assessments. Some of you may have already seen our work in the Lower Mainland and for Northeast BC. We also produced a quite comprehensive report on hydrogen transportation, all of which are available on our website. This work all intends to support the longevity of the hydrogen sector in all four regions by generating interest in the sector. And of course, we acknowledge that there's other important work happening in complementary in central BC, in the Northwest, and Foresight's really trying to tackle the regions of the province that haven't already been examined or already have work underway. So to start, before we get further into the presentation, we just like to get an audience response. First, how familiar are you with hydrogen? We're just going to launch a poll here in a moment. Please feel free to respond. Great, thank you very much. And now we'll move on to talk a little bit about BC and how hydrogen fits in the clean energy transition. So to start, here are two figures that show the breakdown of BC's emissions by sector and over time. Just take a minute to kind of read through and look at the graph. The upshot is really, as of 2020, BC's GHG emissions increased 20% since 1990 and declined about 3% since 2005. As can be seen on the left, the breakdown of sectoral emissions in BC based on 2020 data at the time was transportation at 40%, buildings at about 21%, industry, so that's including things like agriculture, smelting, cement, manufacturing, 20%, and of course oil and gas at 19%. Important note is that the historically rising emissions in the transportation sector and the fossil fuel industry, both of which could benefit from hydrogen decarbonization. So some commitments to reducing emissions that we are aware of now. So at the federal level, there's been a commitment to reduce emissions nationwide to net zero by 2050. This means that by the year 2050, of course, our economy either emits no GHG emissions or offsets emissions. This offset can occur through the technological or nature-based means to sequester or capture carbon dioxide. In BC, we have a commitment to reduce greenhouse gas emissions by 80% by 2050. And of course, the government introduced the Climate Change Accountability Act, which put climate accountability into law for BC and mandated the creation of action plans, monitoring and reporting, and established important interim emissions targets of 40% by 2030 and 60% by 2040. These commitments mean that exploring multiple low carbon energy sources, technologies, and innovations will be needed to meet emissions reductions goals. This is what we're beginning to talk more about, moving away from reliance on carbon emitting energy sources as society and exploring low carbon pathways. The province also has a provincial hydrogen strategy and hydrogen office. And some of the commitments that we'd like to highlight include the commitment to introduce targets for the sale of zero emission medium and heavy duty vehicles, which is of course important for hydrogen. The hydrogen fueling infrastructure program, which supports the installation of hydrogen fueling infrastructure in BC. And to remain a leader in low carbon fuel use and production, BC has increased its target to 1.5 billion liters per year by 2030 and will require about a 10% reduction in the carbon intensity of jet fuel by 2030. Some background on the work in BC on hydrogen. So BC's produced and supported a number of publications on hydrogen, including, of course, the BC Hydrogen Strategy. There's also the Hydrogen Station Permitting Guidebook for BC, as well as the Northeast BC Geological Carbon Capture and Storage Atlas, a really valuable piece of work, and the Carbon Intensity of Hydrogen Production Methods Report, as well as the BC Hydrogen Regulatory Mapping Study. All these reports are really excellent resources, and we encourage you to take a look and review them. The province also supports hydrogen growth through a wide range of the policies and programs that we discussed earlier. So before we move further, I'd just like to note the importance of electricity. Of course, electricity in BC plays an important role in hydrogen development and decarbonization more broadly, especially when electricity is generated from clean and renewable sources such as hydro, solar, or wind. And as many folks know, about 98% of the electricity produced in BC comes from renewable resources. But the question for many, of course, is if BC has abundant renewable electricity, why do we need to consider other technologies such as hydrogen to decarbonize the economy? Well, in many sectors of the economy, electrification does make sense. And should, of course, be the default option for decarbonization. However, electrification is not currently practical for all decarbonization use cases that we have in BC. And so the challenge we're faced with is while confronting an urgent need to drive down emissions, no stone can be left unturned. Limitations for electrification, for example, can be due to the refueling, recharging requirements or other logistical needs of a particular application. An example would be transoceanic shipping, a particularly polluting industry. Based on current technologies in development, you would need an enormous battery that would take up a large amount of space and weight in the ship, which would be difficult for long journeys with recharging requirements. Over time, the technologies will, of course, continue to change and cost reductions will be achieved as we've seen over the last 10 years, for example. But specific applications do require that we target alternative sources of energy for decarbonization. It's also important to note that demand for electricity in BC is expected to grow significantly due to other factors such as population growth, economic development, and the electrification of important sectors such as the buildings and the building sector and industry. BC's utilities do need to procure more power for new projects that meet projected demand and economy-wide decarbonization electrification plans. And the last constraint I'd like to mention is just, of course, that BC Hydro is also considering currently additional constraints such as hydrological changes. So climate change in BC is expected to alter precipitation patterns, increase temperatures, change the timing and volume of spring runoff. These changes can all affect hydroelectric power generation, which relies on consistent water flows. We've also experienced drought conditions in BC, so extended periods of dry and warm weather. This affects the ability to generate power consistently, and BC's experienced some of its driest and hottest extended periods on record in recent years. And lastly, general extreme weather events, so increased wildfires, flooding, droughts can all disrupt electricity infrastructure and damage it. For more information on the future of BC's electricity system, I highly recommend anyone interested to take a look at BC Hydro's latest work on its integrated resource plan, which will be coming out this year. So, in summary, in the situations and use cases where electrification is not possible or economically feasible, low carbon hydrogen could be potentially a complementary solution to electricity. Hydrogen as a fuel has some unique advantages that we're going to discuss in the upcoming sections. And of course, it can be made in BC with a low carbon footprint. So I'd just like to jump to another poll here for you all. Take a moment to read through and respond. Thank you. So first, what is hydrogen? Hydrogen is a gas and is the lightest element on the periodic table. Hydrogen is not found naturally as H2. It's a very reactive element. And so any naturally occurring hydrogen will be bonded to another element. This is important to note because any hydrogen we use is produced. Hydrogen as a molecule is commonly used today as a component of various industrial processes, such as refining, petroleum products, metal production, chemicals, fertilizers, and other processing. The other new use for hydrogen, of course, new being a relative term, is that the carrier of energy. Hydrogen requires an input of energy to produce it. We can then use hydrogen as a low carbon fuel, as we discussed. Hydrogen is be considered as a fuel for important applications that we'll get into further, such as shipping, as I noted previously, but also rail, trucking, aviation. We'll get into that in a bit more detail. So making hydrogen. Hydrogen pathways are often referred to by colors in the media, so we continue to use that vernacular for now. Low carbon hydrogen can be made via pathways, including those pictured here. So blue, green, turquoise, gray and brown hydrogen are not low carbon. They represent some of the existing ways that industries have produced hydrogen and yield significant emissions. The easy way to think about gray and brown, for example, is produced by coal or produced by natural gas without carbon capture and sequestration technologies. We'll speak about each of these pathways in a bit more detail. So first, from hydrogen produced from natural gas. So the production of gray hydrogen through steam methane reforming is currently the most cost-effective and widely used hydrogen production process on the planet. This hydrogen is primarily utilized for producing ammonia for fertilizers, upgrading petroleum products and refineries, but it does have that high carbon intensity. When the CO2 emitted during gray hydrogen production is captured or sequestered and utilized, the resulting hydrogen is known as blue hydrogen. And so the capture and sequestration of CO2 can be achieved through various methods, including injecting that CO2 deep into the Earth's crust. Autothermal reforming is a technology used to produce hydrogen for methanol and ammonia production. It's being proposed as a method to produce low carbon intensity blue hydrogen from natural gas because it enables higher rates of carbon capture compared to conventional SMR and at a lower cost. The other pathway shown here in the diagram is turquoise hydrogen, which is produced from natural gas through a process called pyrolysis. This produces solid carbon as a byproduct instead of carbon dioxide, which can be used in materials manufacturing. This method has the potential to produce hydrogen with a relatively low carbon intensity as a result of having solid carbon byproduct displace carbon from other fossil sources. There are various natural gas pyrolysis technologies available. And these technologies, of course, utilize electricity to drive the process, advantageous in BC with our grid. A note on solid carbon. So amorphous black carbon, a byproduct of this process, is commonly used in industries worldwide for applications such as manufacturing rubber for tires, pigments, polymers, and printing inks. Depending on the source of heat, the process may or may not emit GHGs as discussed, but emissions are significantly lower than what we've seen for methane reformation that I discussed. Waste hydrogen is also a pathway in BC. So waste hydrogen is often produced as a byproduct of various industrial processes, such as chloralkali production, sodium chlorate production, petrochemical refining, and steel manufacturing. In the chloralkali process, for example, hydrogen is generated alongside chlorine and sodium hydroxide during the electrolysis of brine. And similarly, in petrochemical refining, hydrogen is produced during processes like catalytic reforming and cracking. HTEC has an incoming liquefaction facility for byproduct hydrogen in North Vancouver. In BC, the forestry sector is looking at opportunities to reduce emissions, and byproduct hydrogen could be compressed and purified for use at pulp mills, for example. And a local company, Hydra Energy, a BC company, enables commercial fleets to convert existing diesel trucks to run on a hydrogen diesel mix. And they've partnered with companies to use some waste hydrogen to power their dual fuel Class 8 trucks, as an example. That said, an important consideration, of course, is that in the public modeling that we do have available today, waste hydrogen really only represents a small amount of hydrogen consumption and potential production in BC. And so it should be taken with a bit of a grain of salt. Green hydrogen is produced through a process known as electrolysis. This utilizes an electrolyzer to split purified water molecules into hydrogen and oxygen. Unlike traditional hydrogen production methods that we discussed earlier, which often rely on fossil fuels like natural gas, these energy sources have low carbon intensities, some cases close to zero, as we know. The electricity, importantly, does not necessarily need to be grid connected, but that does impact the cost, and we'll discuss that further. And it's important to note that there are electrolyzers already in operation in BC today, and more projects are on the way. So when comparing these production pathways for hydrogen, the two factors that we really need to discuss are carbon intensity and relative cost. As we know, while the use of hydrogen doesn't produce any GHG emissions, the production and the transportation does. And the key point to consider is that when we're looking at the carbon intensity of any hydrogen production pathway, the entire life cycle needs to be considered. So the feedstocks, the transportation emissions associated with the infrastructure, and of course, the production process. For example, this diagram you're looking at here from 2022 is from the Pembina Institute. This shows carbon intensity of different hydrogen production methods. Blue hydrogen in this graph has a greater carbon intensity than green hydrogen. It's of course important to note that, as we discussed already, blue hydrogen, the actual value will depend on the carbon capture efficiency of the technology in question. This is another important graph that I'll hold on for a little bit of time to digest. Obviously, a lot of information on here, but this is an analysis from the BC Centre for Innovation and Clean Energy. And using the GHG Genius life cycle analysis model, the 2023 carbon intensity of hydrogen production methods report provided new information on the carbon intensity of electrolysis, methane reforming, and pyrolysis methods of production here in BC. And so, as I mentioned, while there's a lot of numbers packed into this graphic, it's important to consider some of the key takeaways. So, for example, some things we can note are that liquefied and compressed hydrogen have different carbon intensities in BC under identical production processes. Blue hydrogen could have a lower carbon intensity than electrolysis, depending on the technology, but it does have a far more it tends to be far more carbon intensive rather than the other options. And of course, as you can see, transportation emissions matter a lot, but particularly for blue hydrogen, as it's most likely to be produced in Northeast BC, where there's readily available carbon storage, carbon geological storage, and would need to be transported, say, by truck or rail if pipelines are not an option. You can see how dramatically that increases the carbon penalty of that hydrogen on the left side of those graphs. So I'd recommend checking out that study in more detail, and of course, feel free to reach out to us for any links to some of these reports. We're happy to point you in the right direction. The next is costs, as I mentioned. So this is an older graphic, but just to get us started, from the International Renewable Energy Agency, that compares the cost of hydrogen production from fossil sources and low carbon sources that we discussed, and renewable energy. This is from 2021, as well as the projected cost at the time in 2030. Because of the cost of electricity, green hydrogen was considered the most expensive to produce, and blue hydrogen was considered less expensive due to the cheaper feedstock. But of course, it's dependent on the price of natural gas, which we'll get into a bit. Of course, also requires CCUS infrastructure, and that may be subject to additional costs. And depending on the location and variety of factors, the cost-effective hydrogen production option for BC may vary. This is a more detailed and local study, the 2022 BC Renewable and Low Carbon Gas Supply Potential Study, supported by both Fortis and the province of BC. This showed cost pathways for blue, turquoise, and green hydrogen here in BC. And I'll get into a little bit more detail of each. These are only a couple of the graphs that are in the report, but there is more detail on others. So first, for blue hydrogen, the price of natural gas is a really crucial factor, of course, after the cost of sequestration. Assuming plants, for example, are built at the source, this report found that where natural gas is cheapest and sequestration opportunities are available, any rise in gas prices would be the biggest negative impact on hydrogen costs. This can be mitigated by the expectation that sequestration costs in BC would decrease over time. As well, important thing to consider is the capital cost. Of course, the most significant expense to the need to install both SMR reactors and carbon capture, compression, and sequestration infrastructure. For turquoise hydrogen, the cost of natural gas as a feedstock is the most significant factor as well. Since there's no carbon capture or sequestration required, however, the process is easier to locate and operate. And however, the conversion efficiency is lower than that of SMR, and that leads to higher overall production costs. The most important thing to note for turquoise, though, is the sale of the byproduct solid carbon, or carbon black, as it's sometimes known, could nearly offset these production costs. You'll see that additional green bar on the left. Producing the appropriate grade of carbon and establishing effective sales channels would be crucial for this industry, as the carbon in the feedstock is converted into carbon black rather than emitted, which likely replaces fossil-derived carbon black in industries that use it today. Turquoise hydrogen production is also not affected by increasing carbon taxes, since methane is used as the feedstock, is not subject to the carbon tax. And lastly, you'll see the other chart for green hydrogen. So in this chart, costs exceed $31 per gigajoule, with any incremental savings from efficiency enhancements offset by anticipated rises in electricity rates. Generating hydrogen off-grid, the report found, would incur notably higher expenses. So this is the on-grid 300 megawatt example. This would have significant variations observed between onshore and offshore wind farms. The substantial capital expenditure for wind turbines, for example, and large-scale electrolyzer installations result in considerable off-grid production costs, despite interdependence from the electricity grid. In on-grid production, however, electricity expenses play that pivotal role, but are a bit lower. Conversely, for off-grid setups, one more thing to consider is the producer assumes ownership of the power generation assets, making capital costs for these assets and the electrolyzer farm the primary cost elements, although maintenance and operational expenses are important to consider. So this is a bit of a backgrounder to give you an idea of what the public literature says today, and perhaps what the important takeaways we can take moving forward. Obviously, each of these production methods shows a declining cost over time, and there's a really enormous opportunity on the turquoise side for carbon black sales if that market materializes. So, in summary, electrolysis, reformation, and CCUS and pyrolysis are all possible pathways to produce low carbon hydrogen in BC. Cost and carbon intensity are critical to consider for each pathway. And the simple way to think about it would be that green, as literature shows today, would be lower carbon intensity and higher cost, while blue would be higher carbon intensity, lower cost, and of course, the important turquoise being potentially the lowest cost, but at a higher carbon intensity than green tends to show right now. So with that, I'd like to turn it over to my colleague Aislinn, who's going to chat a little bit about hydrogen transportation and some of the findings from our recent report.
Thanks, Colton. Yeah, so as mentioned, last year we completed a report in partnership with Sacra Davy that looked at the opportunities and risks of transporting hydrogen across BC. Next slide, please, Colton. So transporting hydrogen is an important consideration to the feasibility of the various use cases mentioned. And we need to look at where hydrogen can be produced, where it can potentially be used, and determine how it can be transported and whether or not it makes economic sense. So generally, hydrogen can be transported in specialized cylinder containers by truck or by train, in pipelines or by ship. And hydrogen can also be transported by chemical carriers or as substances that store and transport hydrogen, enabling its future end use. And there are various different considerations with each type of transportation method. So hydrogen can be transported in its pure form as a gas or a liquid. However, there are advantages and trade-offs with both options. Hydrogen is a gas at standard temperature and pressure, but due to its low volumetric density, transporting large volumes of hydrogen as a gas can be quite inefficient. So gaseous hydrogen also needs to be transported under high pressures in specialized containers. Hydrogen can also be transported as a liquid, which is much more efficient for large volumes. But to liquefy hydrogen, it needs to be cooled to minus 253 degrees centigrade. And this process is very energy intensive and can be expensive. Liquid hydrogen also needs to be stored and transported in specialized super insulated cryogenic tanks. And hydrogen is also an odorless and colorless and highly flammable. So there can be explosion risks if it's not handled appropriately. So it's really important that safety measures and procedures are clearly outlined and followed during storage and transportation. And specialized instrumentation may be needed in some cases to detect hydrogen gas in the event of a spill or a leak. But the advantage of transporting pure hydrogen is that no additional conversion processes would be required. So hydrogen can also be transported via chemical carriers. So in our study, we looked at 3 different types of hydrogen carrier: ammonia, methanol, and liquid organic hydrogen carriers. So ammonia is widely used in as an agricultural fertilizer and in industry. So the transportation and handling processes are already kind of well established. The liquefaction process here is also less energy intensive than liquefying hydrogen, but the trade-off is that it is toxic and can harm the environment and human health in the case of a spill or an incident. Methanol is also widely used in industry and it's a liquid at standard temperatures and pressures, so this makes it easier and cheaper for transportation and storage. One drawback is that conventional production methods for methanol can be quite energy intensive, so green or e-methanol production methods are being promoted to reduce carbon emissions associated with the production process. And finally, liquid organic hydrogen carriers are a group of organic compounds that can absorb and release hydrogen through chemical reactions. These are also liquid at standard temperatures, so they can be transported and stored in similar ways to other liquid fuels such as diesel or gasoline. The disadvantage here is that the dehydrogenation process can be energy and cost intensive, And in all of these cases, there are additional steps to release the hydrogen, which is, again, the kind of advantage of transporting pure hydrogen. Next slide. So as mentioned, there are various advantages and challenges with each hydrogen transportation option. And the most suitable option would be dependent on the production site location, the end use requirements, and the volume of hydrogen to be transported. So some of the key considerations for infrastructure include regional differences. So we can see that there's greater availability of infrastructure in more populous areas and areas with existing industrial or oil and gas operations within BC. So in particular, the south and northeast of the province. There will be also variable cost associated with infrastructure upgrades. So again, this is largely dependent on the location requirements, and in particular, new hydrogen pipelines would be very expensive. There is also potential for environmental and social impacts, particularly for the construction of new major infrastructure upgrades. But again, this depends on the location. For some carriers and modalities, specialized containers would be required. So in some cases, these are already available, but in other cases, such as rail transportation, further development and standardization is required. And finally, there is also additional market potential for hydrogen carriers such as ammonia and methanol, as these have other industry applications. So particularly with growing interest in e-methanol as a potential low carbon shipping fuel. So the trade-offs and advantages of each carrier and transportation method need to be assessed for specific scenarios. And factors to be considered include the availability of existing infrastructure, the location and distance between production sites and end users, the volume of the demand, and any end user requirements. So our report also looked to identify hazards and safety risks that are specific to BC. So again, depending on various factors such as the transportation method, location, and hydrogen carrier, there are different considerations to promote safety and manage the risk of incidents. So potential hazards can include environmental factors such as adverse or extreme weather events, or human factors such as accidental releases or road and traffic accidents. The potential consequences of the incidents are also variable. So this depends on the carrier or form of hydrogen and the environment. And this highlights the need for specific risk assessments for individual transportation options. And finally, we looked at incident examples that can indicate preventative measures that can be employed to limit or manage the risk of future incidents. So the report identified key opportunities within BC in terms of hydrogen transportation and provides further recommendations to promote safe and effective transportation across the province. So for more information, the report is publicly available on our website now. So yeah, take a look if you're interested. And I will hand it back over to Colton.
Thanks, Aishan. So now I'm going to talk a little bit about hydrogen demand in BC and potential uses. There's several ways that hydrogen is currently used and can be potentially used in BC. We'll talk about these various applications as well as how the hydrogen use cases compare to other technologies or conventional methods. First, I'd just like to show a diagram. So this diagram is a little controversial in the sector, but shows a representation of potential use cases for hydrogen and scales them from uncompetitive to unavoidable. Just take a moment to digest. It's important to note that BC scenarios might have different results from this example that's based in the UK. So for example, mountainous regions in BC would potentially make hydrogen a better option for long distance trucking. Another example would be BC's large forestry sector could make hydrogen a good option for non-road mobile machinery in remote areas, for example. We'll get into many of these in a moment. So one way we can use hydrogen as an energy source is in a fuel cell. As many of you may know, fuel cells function like a battery. Hydrogen is added as a fuel, which ultimately creates electricity, water, and heat. Fuel cells do not create emissions, air, or noise pollution, and are quick to refuel, similar to conventional gasoline or diesel. Vehicles that are powered by fuel cells are typically referred to as fuel cell electric vehicles, or FCEVs. An alternative technology to consider that we all know, of course, is battery electric vehicles, more prevalent for passenger vehicles currently in BC, require a longer charging period, but they are more energy efficient than an FCEV. Because of the quick refueling times, long range capabilities, hydrogen used in a fuel cell electric vehicle is considered to have a potentially viable use case in those long range applications that I mentioned. So think long haul trucking, but in BC, we could also consider freight rail, aviation. H-Tech, a company here in BC that we'll hear from shortly, has active fueling stations in BC, in the Lower Mainland, Burnaby, Vancouver, North Vancouver, and there's additional planned stations coming, including in Tsawwassen, Surrey, and Vancouver as well. Hydrogen can also be directly burned as a fuel, similar to how someone would combust natural gas. So these use cases include using hydrogen for building heating. This is a proposed avenue that some utilities are proposing to reduce the carbon intensity of the gas supply, predominantly by blending it with natural gas and injecting it into pipelines, which are currently used for heat and power in buildings. There are some logistical and safety challenges associated with this. Some pipelines would need to be retrofitted and new pipelines constructed to accommodate hydrogen gas. The cost of doing this is also much higher than the current price of gas. Fortis BC has commissioned a comprehensive blending study for its distribution network across the province to examine this challenge. However, the recent analysis from the BC Centre for Innovation and Clean Energy did find that blending into the provincial gas grid at safe levels could yield only emissions reductions of approximately 1.4 or 1.7 rather to 4%. So pretty marginal emissions gain, and in some there could be better uses for hydrogen in BC than heating, particularly if we have a limited amount. Some of alternative technologies, of course, electric heat pumps, proven were pretty readily available in parts of the province. Co-combustion technology is another important one to note. So for heavy-duty transportation, I mentioned this earlier, companies like Hydra Energy use this method to blend hydrogen with traditional fuels in heavy-duty engines, and this allows for cleaner combustion on the road and reduce GHGs. Co-combustion is a limited alternative to fuel cell electric vehicles or battery electric trucks in specific hubs, while those technologies are commercialized. So in this kind of transition period that we're in right now, it's a great technology to take advantage of. Hydrogen can also be used to decarbonize industrial processes. So some of these use cases to note would be hydrogen as a fuel, first off. So hydrogen can be combusted directly in boilers, furnaces, turbines to generate heat or electricity without producing carbon dioxide emissions. This could be particularly beneficial in industries such as manufacturing, refining, chemicals production, where high temperature heat is required. Heat treatment processes are common in the manufacturing of metals and alloys, including steel, aluminum, for example. Another would be hydrogen for hydrogenation reactions. So hydrogen is widely used in industrial processes for these reactions. For example, hydrogenation is essential in the production of margarine, edible oils, petrochemicals. These reactions typically require high purity hydrogen, which can be produced via steam methane reforming that I discussed earlier, or electrolysis. Another important one would be hydrogen as a chemical feedstock. So hydrogen serves as a crucial feedstock in various chemical manufacturing processes. For instance, it's used in the production of ammonia, methanol, that Aislinn discussed earlier, and I'll talk a little bit more about, and other industrial chemicals. Ammonia production, in particular, is one of the largest consumers of hydrogen globally. And currently, ammonia is primarily produced via the Haber-Bosch process, which relies on fossil fuels as the hydrogen source. Transitioning to green hydrogen for ammonia synthesis could substantially reduce carbon emissions in that sector. And another that I alluded to earlier is hydrogen for steel production. So steel industry being, steel and aluminum being one of the largest industrial emitters of CO2 due to the reliance on coal and coke in blast furnaces. Hydrogen has the potential to decarbonize steel production through two main pathways: direct reduction of iron ore using hydrogen as a reducing agent, and as a source of heat in electric arc furnaces. Both methods can significantly reduce emissions compared to traditional blast furnace processes. The next I'd like to talk about is renewable energy storage. So as many folks know, hydrogen can be used as a form of energy storage, electricity when generated using renewable sources, can be used to produce hydrogen through electrolysis. This hydrogen can be stored until needed and then used as a fuel for power generation during, say, peak demand times or when solar wind resources are unavailable in certain parts of the province. This is complementary to electricity deployment and particularly for remote communities that aren't grid connected. Can help communities transition away from a reliance, say, on diesel power generation. Hydrogen, of course, is not the only low carbon fuel that's being looked at for off-grid power generation, but is one of the available options that we should consider. And then synthetic fuels. So as we talked about earlier, hydrogen is an essential component in the development of synthetic fuels. These are manufactured, don't come from naturally occurring oil, but have the same properties, so they can be used in the same way as conventional fuels. Synthetic fuels are likely needed as a replacement for aviation and marine fuels, for which electrification, as I mentioned earlier, is not necessarily feasible at this time. Shipping and aviation are considered hard to decarbonize sectors because of those long distances and weight and space limitations. To get into a little bit more detail on the methanol and ammonia pieces, so methanol, common industrial chemical used today, as Aislinn discussed. Methanol is under consideration as it's a commonly produced and transported substance. Reduces carbon and other pollutant emissions in comparison to marine diesel. As I discussed earlier, ammonia, one of the most widely used and produced industrial chemicals across the globe. One of the largest applications of ammonia is, of course, fertilizer production, where it serves as a vital nutrient source for crops. Additionally, ammonia is used for a variety of other chemical purposes. And this just really has the potential to serve as a clean and renewable fuel for that maritime transportation sector I discussed. Lastly, sustainable aviation fuel, or SAFs. It's a term for low carbon fuels produced for the aviation sector. So the non-fossil derived jet fuel, almost identical to conventional jet fuel, can be used as a drop-in fuel. So that means no retrofitting required for those existing engines. There's also potential for hydrogen and synthetic fuels to become a global commodity. So there is growing global demand for hydrogen as countries set ambitious targets to reduce greenhouse gas emissions. Hydrogen is seen as a key enabler of the transition to a low carbon economy, particularly in sectors where electrification or other renewable energy solutions may be, say, challenging or insufficient. Major economies such as Japan, South Korea, China, the European Union have announced hydrogen strategies and initiatives to support the development and deployment of hydrogen technologies. Therefore, there is considerable discussion in the space about laying a foundation for BC to develop hydrogen or synthetic fuels-based export opportunities. The important thing to note, of course, is this is dependent on a surplus. And so if there was a surplus, BC is geographically well positioned to export hydrogen to those major markets in Asia, for example. Deep sea ports, robust transportation infrastructure we have here, road and rail networks facilitate easier access to those markets. So in summary, some of the ways that we can use hydrogen includes in a fuel cell for those transportation applications that we discussed, combusted for building heating or dual fuel combustion, industrial processes such as the making petroleum refining, metals, chemicals, energy storage, and then of course those synthetic fuels such as methanol, ammonia, and sustainable aviation fuels. And really determining the best use of hydrogen depends on a lot of factors that'll be explored in more depth in our reports. So I'd just like to close my presentation with one final poll. So where do you see opportunities for hydrogen in your community based on what you know today, as well as some of the information that we presented? Give everybody a moment to respond to this. And then after you're done responding to the poll, I'll be turning it over to Joshua at UBCO to provide a presentation about some of the work that the university is doing on hydrogen in the interior, as well as some of the perspectives on the Okanagan as a whole. Thanks, everybody. Just stand by for a moment while we switch over here.
Right. Good afternoon, everyone. I hope my slides are visible. Colton, can you confirm?
Yep, looks good.
Okay. So thank you for that introduction, Colton. My name is Joshua Brinkerhoff. I'm an associate professor in the School of Engineering at the Okanagan campus of UBC. And it's my privilege to work and to collaborate with the community in the city of Kelowna, and which is located on the traditional ancestral unceded territories of the Silks Okanagan people, who are the caretakers and stewards of this land from time immemorial. What I want to talk about as a follow-up to what Colton presented is a specific focus, zooming in on the Okanagan region, and particularly identifying how the Okanagan campus of UBC is supporting the Canadian and BC hydrogen strategies through the research being conducted. And so some of this may be a little bit of an overlap with what Colton just shared, but I'm going to zoom in and particularly focus on what were the plans within the Canadian and BC hydrogen strategies and how the Okanagan campus of UBC is supporting our region in achieving those goals. And so as an outline of my talk, some of this is going to be a bit of review, but I'm going to talk about the strategies and what their focuses were, how the research at the Okanagan campus is taking place, and how we're supporting the interior BC within this scope of research. So to start off with, just to kind of carry on with what Colton started and our friends at Foresight, why hydrogen and why hydrogen for Canada and why for BC? Of course, this is motivated by the need to decarbonize. And what we're showing here is the GHG emissions and their breakdown from 2023, where Canada emitted nearly 700 megatons equivalent of CO2. And we can see that it's broken across a handful of sectors, with oil and gas and transportation and electricity consuming a significant portion. And as was presented earlier, some of these sectors, to a greater degree or to a lesser degree, may be an opportunity for decarbonization through hydrogen. And so the Canada Hydrogen Strategy identified opportunities for hydrogen as a part of the pathway for Canadian decarbonization, and also as a part of the pathway for the transition of our economy and for the growth of opportunities within Canada and within BC. And alongside of these opportunities, there is a growth in the demand of hydrogen and a growth in the proportion of hydrogen in terms of the percentage of delivered energy, and correspondingly an increase in the amount of emissions that may be abated through the development of hydrogen technologies and adoption of hydrogen within the sector. And the hydrogen strategy identified, as a prospective opportunity, some hundreds of thousands of jobs that could be impacted by hydrogen positively, both in terms of domestic market and also export markets, and corresponding, billions of dollars in direct revenue. But this is not going to happen just by itself. It needs a concerted effort, and it needs collaboration across a whole range of stakeholders. This was presented already a little bit in the previous work, but to understand the challenges and to understand the opportunities, it really does require a good appreciation of the complex nature of hydrogen as an energy carrier. And I think the right word is energy carrier, because hydrogen is a way in which energy can be stored and carried and then used. And one of the main challenges of that, of course, is that hydrogen is energy dense by mass, but very not energy dense by volume. And this creates challenges for using hydrogen, producing hydrogen, and then using it in end-use applications as well. So currently, the sources of hydrogen predominantly is natural gas, byproducts from other industrial sources, or other energy sources as well. And the end uses, as was presented already, focuses on primarily industrial applications. And so to achieve the decarbonization goals, we need to do primarily two things. We need to find cleaner ways of producing hydrogen at scale that are economical. And then we also need to develop technologies to deploy hydrogen as an alternative for existing incumbent high emissions technologies or high emissions pathways. And so this is what the Canada Hydrogen Strategy lays out as hydrogen's role within an integrated energy system. And maybe the resolution is not so clear, but what I hope to point out is it's integrated. Everything is interacting with one another. And we have the production of hydrogen from renewables. We have the production of hydrogen through alternative uses of existing fossil fuels, such as pyrolysis of natural gas, the sequestration of carbon emissions associated with fossil fuel use, the development and storage of hydrogen and using it for transportation or for material handling or for power production or for building heating, as was highlighted already. And the important comment that I'll make here is these are existing sectors and existing uses to a certain degree that need to come together. And that, I think, is one of the important roles of academia. And I'll just overlay on top of this diagram ways in which UBC is actually already engaged in developing these technologies and then helping these different parts of an integrated energy system to coalesce. And that, as I mentioned, is an important role for academics and academia to assist in a sense, to kind of be the conduit through which existing stakeholders can come together, can work together, and can develop technologies that are allowing hydrogen to integrate within the broad energy system. To focus more on BC specifically, the BC Hydrogen Strategy identifies two primary production pathways for hydrogen that are relevant to BC's electricity grid. And the first one is through renewable electricity sources, such as hydropower or wind or solar or other sources. And then reuse of fossil fuels to produce hydrogen and then sequestering the carbon in some manner. And the role that UBC Okanagan is playing is both in terms of the development of technology for the electrolysis of hydrogen, for the production of renewable electricity, and then also looking at ways in which the pyrolysis of methane to produce hydrogen could also result in value-added products as well. Once hydrogen is produced, it needs to be stored or it needs to be distributed. The UBC Okanagan is also involved in looking at chemical carriers and pipeline storage. We're working with FortisBC to research what are the codes and standards necessary for safely introducing hydrogen into our existing natural gas pipeline, or what are the important considerations for the liquefaction of hydrogen and its storage. What happens if there's an accidental spill of liquid hydrogen or a release of gaseous hydrogen blended with natural gas at high pressure? What are the considerations that need to be done? What new safety measures need to be put in place in order to address those challenges? These are questions that we're trying to investigate alongside partners within the province. And then, of course, after it's stored and brought to the place it's needed, then the hydrogen needs to be used. And so use as a combustion fuel is one idea. Use within a fuel cell for zero emission transportation, then use of low carbon hydrogen to generate new fuels to achieve an overall abatement of emissions, and then other uses. These are also areas for research. And one of the topics that the Okanagan campus is trying to understand is if, for example, you are burning hydrogen mixed with diesel for co-combustion in a heavy-duty engine, how does the hydrogen interact with the materials in your combustion engine? Hydrogen is a very small molecule. It can enter into the metal matrix of that material. It can aggregate in microcracks, and it can reduce the ductility of that material in a reversible manner or in an irreversible manner. How does that impact the longevity of these materials? And also the safety associated with these technologies. And so these are important questions to understand, and this is work that's being done within the campus, with the overall objective, of course, of helping the province achieve its emissions reduction potentials. And this is the way that the BC Hydrogen Strategy sees the possibility for hydrogen achieving a reduction in up to 60% reduction in transportation and other areas as well. Whether these can be realized is still to be determined, and it requires continued work. So achieving this BC hydrogen strategy, there was a plan that was laid out alongside a BC hydrogen study in 2019, and it laid out the achievement, like the pathway in the following ways, right? First phase is development of supply and infrastructure. The second phase is the commercial introduction, and then the third phase is in the commercial expansion. And we're already 5 years into this plan, and so there's probably room for tweaking or adjusting. But in the context of this plan, I wanted to highlight how work within the UBC Okanagan is helping contribute to this goal and follow the kind of the development plan for hydrogen within the province. And so to do that, I'm going to overlay research topics that are ongoing with partners on top of this plan to show alignment within the provincial hydrogen strategy. So the first one is we have a Fortis BC research chair, that's Professor Huagi, working with Fortis BC to look at ways in which existing electricity grids can be deployed in a smart way to support the decarbonization of our electricity supply, which is critical if that electricity will be used for production of renewable hydrogen. We are working with Fortis BC. This is actually 6 researchers understanding blending of hydrogen into natural gas from a whole host of different angles, both the production of hydrogen in a renewable way, the injection process and ensuring that is done in a predictable way and a safe way. When you introduce hydrogen, you're changing the energy mix because of the different energy behavior of the gas. That changes the flow rate, which changes the production loss, the transmission losses, and so forth. And so this needs to be modeled. Also understanding what are the potential safety considerations if hydrogen is accidentally released, if there's a failure in the grid of the natural gas grid. Of course, when you introduce hydrogen, it burns differently than natural gas. And this needs to be understood both from a small appliance application, like a boiler in your home, or from a large appliance, like a gas turbine combustor powering your gas pipeline compressors. So this is also another area for research. And then, of course, the material embrittlement, which may occur as the hydrogen interacts with materials within the natural gas grid. So this is another area for research that's ongoing. The next, of course, is how do we use hydrogen in transportation to decarbonize? Within the Okanagan campus, rail decarbonization has been a particular focus, and I'll talk briefly about that in a minute. The use of hydrogen in combustion applications, both in terms of aviation, stationary combustion applications from small to large scale, as well as combustion applications in heavy-duty transportation. These are other important topics. And then, of course, the development of low-carbon synthetic fuels from the hydrogen that's produced, which we can then deploy in aviation and other sectors as well. Aviation is one that's particular interest within the School of Engineering. The production of green hydrogen, particularly not using electricity, but using waste heat, a so-called thermochemical cycle, is another active area of research within the school. And this provides another alternative pathway for producing hydrogen with less electricity requirement, and takes advantage of waste heat sources that may come from cement factories, smelters, pulp and paper mills, etc., which may be particularly well suited for the interior of BC. Mentioned already is the important work around the materials for storing, transporting, and using hydrogen, which is another important area for research. So from these, I'll just highlight a handful of important activities that are taking place. The one that was mentioned already is a project with Fortis BC, in which we're studying a whole host of different topics around blending hydrogen into natural gas pipelines, from the injection and transmission aspect to flammability and safety risk associated with the blending, the detection of leaks of hydrogen in a high specificity and high throughput manner, the material embrittlement concerns that might come out of the injection process or blending process, developing a digital twin, if you like, of this whole blending system so that we can see how does the grid as a whole provincial entity respond if you introduce hydrogen and change the composition of the energy mix, the combustion aspects, and then Some applications may not tolerate hydrogen in the mixture, particularly if the gas is being used not for burning, but for as a feedstock for some industrial process. And so how do we then remove the hydrogen after it's for certain customers who may not tolerate its use? So this is an ongoing work with Fortis BC. And just to highlight one of the results, this is a computer simulation looking at the way a high pressure jet will behave if it was released following an accidental puncture of a high pressure pipeline. And on the left-hand side, the video shows the development of this jet when you have a 20% by volume hydrogen mixture at low pressure, 0.4 megapascal, typical of a distribution pressure line. And on the right-hand side, the same jet, but at a transmission pressure, 4 megapascal. And we can see this is showing the instantaneous pressure field in the jet. And the behavior of the jet is quite different. In the low pressure condition, it forms a high velocity jet with interacting pressure fluctuations that maintain a high velocity, and mixing is delayed. In the high pressure condition on the right, you have this, what's called a Mach cone, where you have an abrupt deceleration of the jet, and the turbulence enhances the mixing. And all of this has a difference on the impact of the safety precautions and classification of equipment, etc., in the context of responding to the accidental release. Understanding this behavior using computer simulations is critical to safely deploying hydrogen within the natural gas grid. I did mention the use of hydrogen for heavy-duty decarbonization. This is a project with Southern Railway BC, which is in New Westminster, and Hydrogen in Motion in the Lower Mainland, where the first rail switcher locomotive hydrogen rail switcher locomotive is being developed. And this is a real-world application in which diesel engine was removed from a switcher locomotive, which is a small train engine that moves cars in a yard. And we replaced that with a hydrogen storage system, a hydrogen fuel cell, and batteries, and are now testing the use of hydrogen for this application, which has a number of benefits, not the least of which is noise and emissions within an urban environment, because this is operating within a city. So just to then put a conclusion on the work, how is the university supporting an interior hydrogen hub? And barriers to achieving our hydrogen economy is clear. If we want to achieve the 2050 goal of 20 megatons of hydrogen per year, the amount of electricity required, if it was all done through electrolysis, would be the equivalent of more than 200 Site C dams, which is really unfeasible. And if it was all done through natural gas, then this would be the equivalent of the gas consumption of 43 million homes. Also not a high level of barrier, which means that there's the need to work together to develop low carbon energy sources, to develop the technology around that, to create the economic and investment opportunities required to support the policy and regulations, which of course needs science to guide that, and the codes and standards development to support the safe adoption of these technologies, and then of course public awareness. And there's a role for everyone in achieving and overcoming these barriers. And when you look at the particular activities that are involved, we can see the important work of governments and industry and utilities and Indigenous communities and NGOs, as well as the academic sector, with a particular emphasis of academia's important role for cross-sector collaboration, for generating research and funding that research, for building consortiums and developing the industrial partnerships needed to grow regional hubs and domestic flagship projects that can then grow and scale up to support the provincial and Canadian goals. And so what is currently underway within the Okanagan campus is the development of a hydrogen training and research center, which focuses on supporting a regional hub for hydrogen research and also supporting the commercial development of hydrogen through the adoption, through the dissemination, creation of research, and then adoption of that research within the technology of our industrial partners. And so the focus within this particular hub and the place of the research strengths of the campus around blending of hydrogen into natural gas, combustion of hydrogen, materials for storing hydrogen and transporting it, et cetera, applications, particularly in the transportation sector, and then also on the safety storage side, and also storage and safety associated with end uses. And so how is this hub going to support, well, how is the campus going to support hydrogen development? This is a very busy diagram, but what it shows is research activities of different professors in orange interacting with different companies around different topics. And the emphasis that I want to highlight in this is to show the interconnectivity of all the different research topics, all of the different academic partners, as well as all of the different industrial end users and participants within this technology system. And that's the whole point, I think, of a regional hub, is that it requires a lot of interconnectivity and a lot of work of building partnerships. And that, I think, is the most important contribution that the academic sector can bring to the hydrogen space. And so I'm very keen to continue working with our existing collaborators and would love to build new collaborations as well, all for the goal of advancing hydrogen work within the region, the interior of BC, within BC writ large, and of course, Canada. And so to move forward together requires everyone at the table. We need to grow. We need to build these strategic partnerships. We need to engage with one another, developing these technologies. And I'd be very open to hearing from you if you have ideas in which you could contribute to this effort together. So please reach out to me with your interests. And thank you for your attention.
Wonderful. Thank you very much for that great presentation. I'd now like to turn it over to Rachel Beckley and Jim Shen at HTech. We're going to give a short presentation on their work on Vancouver Island.
Great, thank you. Let me just pull this up. Okay. Hi, everybody. So my name is Rachel Beckley. I'm a manager of government relations at HTech, and I'll be presenting with my colleague Jim Chen. He's a project manager for our Clean Fuels team, and he'll take over some of the slides for me in a little bit. Before I begin, just want to acknowledge that we're both presenting today from the traditional and unceded territories of the Squamish, Tsleil-Waututh, and Musqueam First Nations. So just a little bit about HTech. So HTech is a pure play hydrogen infrastructure solutions company. Our main focus is decarbonizing the transportation sector. So all of our projects are focused primarily on end use transportation applications. We started in the light duty market. So we have 6 stations that are operational throughout BC, a few in the Lower Mainland, one up in Kelowna, one in Victoria, and then we operate another station out of UBC, the Vancouver campus. We are comprised of about 130 employees, and we have dispensed over 100,000 kilograms of hydrogen through our station network since those have been operating. So our projects have the potential to reduce up to 400 kilotons of CO2 emissions by 2030. And I'll speak to what those projects look like shortly. So we're comprised of 3 business units. So our Clean Fuels team handles our production facilities. So we are developing 3. 2 are electrolysis and 1 is byproduct capture. One of those electrolysis facilities is going to be in Nanaimo. And then we have our stations and distribution team, which is building out our network of stations, both for light duty and heavy duty vehicles. And then we have a transportation solutions team that works with fleet operators to lease these fuel cell electric trucks for them to integrate into their fleet to help them decarbonize their operations as well. So we work across the entire value chain. As I just mentioned, we do production, we distribute the hydrogen from our production facilities to our stations, and then we dispense them into the cars and trucks. So H2 Gateway is sort of what we call our hydrogen hub program, and it involves 4 hubs throughout the province. And our 2 sort of focus hubs at the moment are Lower Mainland and Vancouver Island. And then we'll eventually move towards the interior and up to Prince George as well, and have some connection to Alberta. So this will have a number of heavy duty fueling stations, some light duty stations, 1 liquefaction facility in North Vancouver. That's the byproduct capture one, and then 3 electrolysis facilities. And it will also include 100 fuel cell electric trucks to start. That will be leased through our vehicle leasing corporation, and those will move throughout the province. So this just gives a little bit of context into our projects in Nanaimo. So I'll pass it over to Jim now to talk about that.
Great, thanks, Rachel. Good morning, everyone. I'm going to give you a brief overview of our Nanaimo clean hydrogen production facility, which will be Vancouver Island's first at-scale hydrogen production project. So this will be a 2 metric tons per day clean hydrogen production facility, which will be co-located within the Harmac Pacific pulp mill in Nanaimo. The facility will be capable of producing hydrogen by electrolysis, so using electricity to split water molecules into hydrogen and oxygen gas. And we plan to be operational in Q1 of 2027. At full capacity, this production facility will be capable of supporting and supplying 50 heavy-duty zero-emission trucks, or the equivalent of 4,000 passenger vehicles. It's projected to also generate more than 14 jobs in BC, which is directly related to the build and operation of the plant. And in terms of GHG emission reductions, it will be approximately 15,000 tons of CO2 equivalents per year at full capacity, which aligns with the City of Nanaimo's Climate Action Plan. So I want to make sure we give a big thank you to our project partners on the bottom there, Natural Resources Canada, Canadian Infrastructure Bank, and the Harmac Pacific Pulp Mill for the support for the project. Next slide, please. Just giving a brief overview of the major components of the facility. So starting from the bottom there, the switchgear and the electrical room will be directly connecting with the Harmac Pacific Mill's electrical system. So we'll be getting medium voltage power through the pulp mill, and that'll be feeding the 2 modular proton exchange membrane electrolyzers that we purchased for the project. So we have 2 1-ton per day electrolyzers, and as I mentioned earlier, the water will be split there. Hydrogen will be created at approximately 30 bar, and that will be fed into the compressors, which will bring the pressure up to 450 bar. And that will be the distribution voltage which HTEC uses to fill our distribution trailers, which we pull up in the filling area there. They'll be filled, and then once they're full, they'll be moved off-site and will be used to supply our stations and our other offtake partners on the island. Slide, please. Brief overview of where we're at for the project. So as of now, we've procured most of the major equipment already. We have existing site license agreement with Nanaimo Forest Products, which is the owner of the pulp mill. We completed the feed study, the front-end engineering design study, and we just submitted for the building permit with the city in last month in March. We're progressing through detailed engineering right now, and we expect to be completed that in July of this year. And we have approximately a 1-year period for construction, installation, commissioning, which leads us to January 2027, which we anticipate to start producing this facility. I'll pass it back to Rachel for the next piece.
Thanks, Jim. So I know we're here today to talk about sort of opportunities for what a hub might look like. So because HTEC is focused on transportation applications, obviously we see the biggest opportunity being in heavy duty commercial trucking. We are going to be developing a station in tandem with our production facility just to have supply close to dispensing. And that local supply will really help support the adoption of fuel cell electric trucks on Vancouver Island, instead of having to transport the fuel via ferry from North Vancouver to Vancouver Island. So our transportation team is working to sort of bring that load to station by partnering with fleet operators who'd be interested in leasing vehicles. Other opportunities are transit fleets. This is typically who will first adopt hydrogen vehicle technology. And there's a lot of these cases happening in Europe and the US, and it works really well because of the return to base fueling operation. And then, of course, there's light duty passenger vehicles, which are already on the roads. We have a station in Victoria, and we have plans for more. And there's also a real opportunity here for light duty fleets. So car shares, delivery services, and vehicles that use a lot of fuel. So what we have done is we've created a wholly owned subsidiary called Vehicle Leasing Corp. And why we did this is we're sort of trying to solve the problem of the chicken and the egg by creating both the supply and the fueling as well as the end use demand. So as part of the H2 Gateway program that I mentioned earlier, we'll have 100 trucks coming to BC. HTEC will own those trucks and we lease them out to operators who want to have them in their fleet. And then that reduces the need for operators to put up a large upfront cost to purchase a vehicle brand new, and allows them to sort of test out the technology, see how it fits with their operations, and we'll gather lots of data and information that will help sort of bring these to more commercial operation. And our full package includes preventative and corrective maintenance services and adoption support. And we also will be working with a safe maintenance facility out of Abbotsford called Velocity, and we've already trained their employees on how to operate and maintain these vehicles. So just to end off, what does a hub sort of look like? So this is actually an example of what we've been doing in the Lower Mainland, and this is a small scale hub, but you kind of have to see it happen in real time before you can kind of bring it to scale. So this is sort of exactly what we have planned for Vancouver Island as well. But we recently started operating our electrolysis plant in Burnaby, which was a big milestone for us. Previously, we were purchasing hydrogen from third-party suppliers to fuel our stations, and now we have our own supply of low carbon intensity hydrogen. We'll then be supplying that to our first heavy-duty fueling station, which will be located on Tsawwassen First Nations land, and that's in partnership with the nation and Parkland, and that's operating near the port, so it will be used for a lot of port applications as well. And this is BC's first heavy-duty hydrogen refueling station, and it's currently under construction, so hoping that that will be opening by this summer. And then aside from the 100 trucks I spoke about, we have 12 trucks coming that are already, actually 5 are already delivered for pilot purposes. And this has been supported through the province of BC. So 6 of those will be used at the port and 6 will be used just for heavy duty trucking around the Lower Mainland. And then, as I mentioned, we partner with a safe operator who helps maintain the trucks. So this is just a bit of an example of what a hub might look like for a transportation application. And yeah, I think that's all we've got. So thank you. Thanks, Foresight team, for allowing us to present today, and happy to answer any questions as they come up.
Thank you very much. I'd just like to say another huge thank you to Rachel and Jim for the great presentations, and Dr. Joshua Brinkerhoff for also sharing the great work that's happening at UBCO and in the interior. We're going to be closing off there, but of course we welcome your feedback and to reach out with any questions you have. Foresight's work is ongoing, and we'll be producing our final reports for the Vancouver Island hub and the interior hub to be released in July of this year. And all of our additional reports that have been completed to date that we've discussed already today are available on our website at any time. So thank you again for attending today. We really appreciate it. And we hope to hear from you in the future. Thanks, everybody.